Welcome back. We're studying related rates. And if you're following along in our notes, I'm going to do the next couple of problems out of order. So I'm going to work on example 4 next, which is a very classic related rate problem. This is describing a ladder leaning against a brick wall or just a wall and touching the ground. And imagine the base of the ladder, the part touching the ground, imagine it sliding away from the wall by someone pulling it at some rate of speed. And of course, because the ladder is not going to change length, as this section moves away from the wall, the top of the ladder is going to come crashing down the wall. And I think you can imagine the faster I pull this away from the wall, the faster this will come down. So there is a relationship between the rate at which we pull away from the wall and the rate at which the ladder comes down the wall. And we want to see what happens here in the situation where in this one it says we're going to pull away from the wall. This is going to pull away from the wall at 3 feet per second. What we want to see is how fast is this tip of the ladder coming down the wall. At exactly the instant that it's 5 feet. At the exact instant that this bottom of the ladder is 5 feet from the base of the wall. Okay, now remember, it's not always going to be 5. This distance started off being less than 5. We're going to pull away from the wall, and at some instant, it's going to be exactly 5 feet away from the wall. We're going to analyze the problem exactly then. Okay, so this 5 feet is not a constant value. It's just the spot where it's going to pass through that instant, and we're going to analyze the rates exactly then. What we need first is an equation relating the distance that this point is from the wall. And remember, that is not a constant distance, so we're going to label that as a variable x. As that distance moves away from the wall, this top ladder is going to come down the wall, and that's going to be a changing quantity too, so let's call that variable y. And now there's also the length of the ladder, but we aren't going to use a variable for it because the ladder is not going to change length. The ladder will remain 13 feet the whole time. But let's think about this. We're going to assume, of course, that the wall is perpendicular to the ground. And now, you should see a triangle right here made by the ladder and the wall and the ground. We know it's going to be a right angle. And now the equation that I can think of that relates the 3 dimensions in this triangle, because the height of the triangle, the base of the triangle, and the hypotenuse are all related by the Pythagorean theorem. And if I look at the way I've labeled it, I know that x squared plus y squared is going to always equal the hypotenuse squared. And I know the hypotenuse isn't going to change, so I'm going to go ahead and write it in 13 squared. But x and y are changing, so they're going to be needed to be treated as functions or variables. Remember, it's implied here that x really means x as a function of time. And it's also implied that y is a function of time, because these are moving at a particular rate. So at any given moment, they each have their own value and each have their own rate. So now we're going to apply a derivative to both sides of the equal sign. But it's with respect to time, because these functions are functions of time. So now each derivative requires the chain rule. So the derivative of the derivative of x squared is 2x to the first times the derivative of x, which I'm going to write dx dt. The derivative of y squared, remember that's the function y squared, so we use the chain rule again, 2y times the derivative of y. But it's on this side, I just need to know that this is a constant. So 13 squared, the derivative of that has to be 0 because that was a constant. Now, the question in part A was how fast is the top of the ladder sliding down the wall? Well, that's this distance right here. So we're trying to find We're trying to find the rate at which y is changing. So we're attempting to find dy dt. We're given that the base of the ladder will be 5 feet from the wall. That is x. We're also told that we're sliding x away at a constant rate of 3 feet per second. Now, so I've set everything up here, but there's one thing left in this equation that I do not know yet, and that is I don't have a number to put in here for y. I encourage you to pause the video right now and decide for yourself. If I know that the ladder is 13 feet long, if I just freeze the action for a moment and imagine that the distance here is 5, how would you know what the y is? I encourage you to pause the video and think about how you would do that. So I'm going to ask you to check your own work here. If I were just to freeze the picture and imagine that the ladder is indeed exactly 5 feet from the wall right now, then I can just imagine the triangle formed at this instant contains 13 and 5, and I just want to find y. Well, again, I can just use the Pythagorean theorem, because 5 squared plus y squared has to make 13 squared. So that makes, if I do the math here, this is 169 and this is 25. So y squared is 144 and y is going to be 12. So now I have everything to put into my derivative except for I'll be finding dy dt. So when 2 times x is 5 and dx dt is 3, and then 2 times 12 times dy dt equals 0. I'm solving for dy dt. So let's do the math here first. This is going to be 10 times 3, so 30 plus 24 dy dt equals 0, which means I'm going to subtract 30 and then divide by 24. So dy dt is negative 30 divided by 24, and if I reduced it down, I can divide everything by 6 here. Or that's negative 1.25. Now, what would the label be? If we had put labels in all of the work as we went, the label would have spit itself out here at the end. Or I can just see that y is the height of the ladder, which would be measured in feet, and the time is measured in seconds. So this rate will be in feet per second. Now you notice the answer was negative, and we talked about in the last lesson that a rate could be negative. Like, for example, if we were describing the moving particle, the velocity can be negative to indicate that the direction is to the backward side or to the negative side. Or in this case, the negative direction would be down, and so this makes sense that the rate would be negative, indicating that the ladder is moving down the wall as opposed to going up the wall. So the negative indicates the direction. It's moving down the wall at 1 1/4 feet per second. Now, part 2 of this problem is the same ladder, same rate that the ladder is being pulled away from the wall. Same everything. In fact, we're going to freeze the problem again when the ladder is 5 feet from the wall. But what we're analyzing this time is the area of this triangle that I see under the ladder here. Okay, because as the ladder pulls away from the wall, the height will be decreasing and the base will be increasing. So for different combinations, the area will be different. So this time I need to pull from geometry how I find the area of a triangle. If I again label the base direction x and the vertical direction y, area of a triangle is 1/2 base times height. So I'm going to have 1/2 xy. And so now we want to find the rate at which the area is changing. We want to find dA dt. Given, again, that x is 5 feet from the wall. We're given that the rate of change of x is 3 feet per second, just like before. Just want to double check that. Yes, 3 feet per second. And I already know also that at this instant, when the x was 5, we learned from the previous problem that y was going to be 12 feet. Okay, so that number wasn't given, but it was found in the previous work that when x was 5 and the ladder is 13 feet, the y is 12. We also found in the previous problem the rate of change of y at this exact instant was negative 1.25 feet per second. Okay, we may need all of those quantities, so I'm just going to make a note of what we learned in the last one. And then what we're supposed to find is the rate of change of the area of that triangle. So let's apply a derivative now to both sides. On the left side, obviously, we're just going to get dA dt. But now on the right side, I actually have a product, so don't forget we're going to need the product rule here. And if you'd like, I don't need to put the 1/2 in there. I can leave 1/2 as the constant multiple. And we're just going to work out the product rule for the derivative of x, y. So that's 1d2 plus 2d1. That would be x times the derivative of y, and then y times the derivative of x. So notice the thing I want to find is dA dt. And over here, I need a combination of both x and y and dy and dx. So we're just going to put all of those in there and then calculate the final answer. So at the instant that x is 5 feet, and from part A, we learned that at this instant, the rate of change of y is negative 1.25. And at that instant, the height of the ladder there, y is 12 feet. And dx dt is 3. That's the given rate. So all that's left for us to do is do this calculation, and I'm going to do that with my calculator. So I'm going to take 5 times negative 1.25 first. I'm going to add to that 12 times 3. And then I'm going to divide that by 2 or multiply by 1/2. So I got for my final answer here 14.875. Now, if I had put units in all of these numbers ahead of time, I would have already known the unit, but we know it anyway because the area is measured in square feet, the time is measured in seconds, so this rate should be square feet per second. Well, I hope this helps you guys. There's a few problems on the assignment sheet that are similar to these, and some that are not. But if they're not exactly the same as these, I remind you that you apply the same principles. You have to know an equation that relates to changing quantities and differentiate with respect to time. I hope this helps you enough to get a good start. Please stay in contact with me if you are needing assistance on any of the other practice problems. But I'll look to hear from you soon. Have a good day.